Hello, and welcome to Tech to Tech presented by KYZEN, where we will explore common cleaning questions and answers. Let's get started. I would like to introduce KYZEN's own Rich Burke.
William, thank you, and welcome everybody to today's Tech to Tech session. Today's session is going to focus on the underside wipe process, stencil cleaning, and before I get started, I do want to kind of give a thank you to ITW. ITW participated in this study, so without their help, the study would not be possible. So when I say ITW, this was actually the MPM division of ITW. So again, thank you to you guys. When we look at an underside wipe process in terms of the cleaning step, the industry typically focuses around the solder paste itself and removal of the solder paste from the apertures and undersides of the stencil. In this case, we're going to look not only at that, but more importantly, we're going to look at the flux residue removal of that step. The second thing that is important to make note of is that, like many things over time, things evolve, and I say things evolve meaning the cleaning agents in this case have evolved over time, as well as the delivery system in the screen printers for the underside wipe process, and with that comes the need to reevaluate where we are and understand how to optimize this process given the new materials and the newer delivery systems that are in today's screen printer systems. Next, I have frequently asked questions, and I'm not going to go through and answer these specifically right here, right now. These are typically done at the end of these sessions, but in this case, the purpose here is to really identify these questions, and you'll see that these are being answered as we go through the process. So the first question that we're trying to get answered here is, what is the ideal or the optimal solvent contact time to effectively remove the flux residue? The second question that we're going to try to answer throughout the course of the series of the testing was, are today's currently used wipe sequences achieving the highest level of cleanliness and therefore defect reduction when it comes to the print process? And then the third and last question that we were trying to get answered is the utilization of solvents, and do those in fact impact negatively the print process itself? So again, throughout the course of the testing, these are some of the things that we're really trying to get answered. Lastly, before we just jump into the testing itself, I want to highlight some of the key findings, because I think it's important to kind of make note of this in the very beginning, because a lot of these findings were, I would say, quite surprising. And I say that when you work with a senior applications engineer in printing that's been doing this for many years, and their eyes open up, it really does tell you that you're looking at something that was unexpected. And so we want to highlight these key points really before we get started. So the first is the wipe sequence itself is critical when it comes to cleaning of the flux in terms of flux component of the solder paste. Second is the conventional underside wipe process parameters do not actually or are not optimal when it comes to cleaning of the flux residue. Third item is when we look at the saturation of the paper, we actually found that increasing saturation is better than decreasing saturation. So a wetter paper is better than a less wet or drier paper. The fourth item that I think is very important to make note of is that slower gantry speed is better in performance than a fast gantry speed. So this really speaks to two things, right? Increased solvency of the paper or saturation of the paper, and increasing the exposure time of the paper to the inside wipe. Two important aspects. The next item to make note of is that in the testing we did find that the ideal sequence was a vacuum solvent sequence. And again, this is not, up to this point, has not been a customary sequencing, but that really did make a big difference. And then lastly, it's important to make note that through SPI, solder paste inspection, we did validate that it is more effective to run a solvent process than that of a dry wipe process. So again, this is some key points that we'll see as we go through the study, panned out, if you will. In terms of materials, I won't go into everything on this slide. There's a lot on here, obviously, but key points here are the testing was done with an industry-wide, industry-recognized screen printer, automated screen printer, used an SMTA test vehicle. Stencil was a nano-coated stencil, a Type 4 solder paste, no lead. We did apply a UV tracer to the solder paste so that we were able to see that under black light condition. So that actually was part of the inspection process in the first phase of the testing. And then lastly, the solvent that was used was a non-water-based material. So here you just kind of see what I'm talking about when I say using a UV light. So these are examples of assemblies that were printed and put in and underneath the UV light, we're able to see the remaining residue. You can see that kind of streaking in here and streaking in here. So that's really what we're looking at under UV conditions. So it made it very easy for us to visually understand what was really happening in terms of the cleaning process. So next, you'll see a series of 5 different tests that were performed, and I'll go through each of these with the results from each of these particular tests. So the first one is really to establish the baseline of the testing that's to go forward. So number 1 is really to define the machine parameters. Again, I won't go through everything on this slide. Make note that the speed of the print process in this case was 1.5 inches per second, because that will change as we go forward, but so I want to make highlight of that. Next, just to look at the wipe definitions as we define these. So first we have a dry wipe, and we refer to that, or that consists of a vacuum and a dry. The solvent wipe consists of a solvent vac dry sequence. The solvent bar speed that's used here for default was 3.5 inches per second, and then the gantry speed used is 2.0 inches per second. So let me back up for a minute. When I say solvent bar, this is the mechanism for this particular printer to deliver the solvent to the paper. And then, of course, the gantry speed is the speed by which the underside wipe gantry is operating. So test number 1, this baseline test, is broken into 2 parts, and this is so that we can determine whether or not it's necessary to run full print cycles, or can we replicate the print process with a knead stroke process. So the first phase here was to print 15 consecutive boards, and then on the 5th and 10th board do a dry wipe, and on the 15th board do a solvent wet wipe process. It's important to note that for each of those steps, so the 5th, the 10th, and the 15th printed board, the stencil was removed and inspected under the black light before and then after the wipe sequence happened, so that we could see the effect of that particular wipe, whether it was the dry wipe or the solvent wet wipe process. So that was phase A. Then we want to do a comparison between the printing of those boards to doing it through a knead stroke process that would facilitate a faster overall testing time. So we replicated that. The other thing we did notice during this phase of the testing was that print speed that I mentioned earlier of 1.5 inches per second was too slow, and that caused overfill of aperture. So the speed was then increased to 2.5 inches per second. So the results of this testing did show us that we were able to replicate the results of test A through the knead process of test B. So going forward, the knead process would be utilized, again, to help speed things up. The second thing, very importantly noted here, was that the standard process of a wipe sequence was not successful in removing the flux residue. So this is really important to establish this right from the beginning, and we'll now have to work towards improving that, and we'll go through that now. So first, you can see some imaging, and this just shows what I was talking about a minute ago, that there's a similarity between the printed assemblies after the 15th print. You can see some streaking in here, and similar, you see that over here through the the boards that were processed under the need step cycle. So test number 2, this is looking at the effect of the solvent bar speed. So when I say again the solvent bar speed on this particular printer, like I say, the solvent bar is the mechanism that delivers the solvent to the paper. So in this case, we want to determine what's the right amount of saturation of the paper, and again, that's controlled through the speed. So the minimum speed that's tested here in this particular case was 3.5 inches per second. That up until now has been very common on what one would run. Oftentimes when people look towards the application of a wet process, the thought is lower amounts of material being better than higher amounts of material. That's kind of the conventional wisdom, if you will. The gantry speed, again, that's utilized here is the 2.0 inches per second. So you can see that the solvent bar speeds that were varied or evaluated was 3.5, 4.5, 5.5, and 6.5 inches per second. And again, like I say, lastly, the faster that speed, the more solvent delivered to the bottom of the paper, so increasing saturation as we go up in speed. So what we can clearly see in this testing, in the results, was that more solvent applied yielded a better cleaning result. Prototypical guidelines would say minimum amounts of solvent, and that clearly did not show an adequate cleaning result. So that is definitely something that was proven to be incorrect during this phase of the testing. So increased saturation better than lighter saturation. So clearly the 6.5 inches per second setting was ideal and used as we go forward in this testing. It is also noted that the dry wipe sequence, which would be a vacuum dry, was not very effective. In fact, what we were really looking at is likely the vacuum jarring the solder paste out of the apertures and then smearing that across the stencil. And you can see that here if you look at these images. So after the fifth printed board, we inspect that stencil, we can see streaking. After the 10th, we see streaking here as well, and that streaking is gone when we apply the wet wipe process solvent. So clearly the addition of the wet wipe or the solvent step was and does play an important role, and increasing that solvent application is important. So the third phase of the testing was to understand the gantry speed. So we just talked about the saturation of the paper being important and more being better. So now we're going to look at the gantry speed. And again, this is where we're taking the saturated paper and exposing it to the bottom of the stencil. So we want to understand whether the amount of exposure time, what role that plays, if you will. So that's what this testing is trying to do for us. So you can see these speeds are varied from 2 inches per second down to 1.5 inches per second, 1, and then half an inch per second. So again, the standard today would be 2 inches per second. That's a kind of a machine default, if you will. And you can see we're decreasing that by half an inch per second increments. Again, keeping the solvent bar speed at 6.5 as we learned in the last test. The results of this test, again, clearly showed us that a slower gantry speed is beneficial in terms of the wet wipe process. So, again, it kind of makes sense, right? We want to have enough material applied to have solvency of the paper, and then it's very important to give that solvent exposure time adequately, such that the solvent is able to solubilize the flux residue and help it to be removed from the process. It was clear that the default speed of 2 inches per second was not effective at all in removing the flux residue, or ineffective, I should say, at all. It did something, but it was not adequate. Without question, 1 inch per second was good, showed clear improvements, but half an inch per second did in fact give us the best overall result. Now, obviously, that's good news in terms of defect reduction, good information, right? Good news. However, it does mean there would be a cycle time hit. So that's kind of the bad news of what was learned in this test. Now, that being said, because we're more effective or more efficient in terms of the actual cleaning step, it's very likely that the total cycle time can be balanced by increasing the number of prints between the actual wipe requirements. So it may actually give you well, it would likely give a better result and not have a hit to cycle time, is what we would say. The other thing I think that we saw from this, or an observation from this phase of the testing here, was that it appears as though the vacuum wipe step itself is a contributor to the flux being smeared on the bottom of the stencil. And again, like I say, the vacuum wipe is doing what it's supposed to do. It's drawing the remaining material out of the apertures, and if it's not adequately solubilized, it will then smear across the stencil. And like I said, so that's what we believe we were seeing, and we need to kind of better understand that. So the next phase of the testing is to look at the different wipe cycles and combination of those cycles to determine what is ideal, and that's really what we're looking at this next stage. So here, like I say, we're looking at wipe sequences, right? So we're going to run 4 different combinations. And before I jump into those, I just make note that, again, the industry guidelines going into this testing would be start with a solvent wipe, regardless of what's after that. So solvent wipe in the beginning and not towards the end. That's kind of what the convention wisdom has been. And secondly, again, like I mentioned earlier, lower saturation would be the guidelines prior to this testing, right? That was what the industry would say is minimize the amount of saturation of the solvent. We obviously talked about that. That was already been proven not to be an accurate thing, or a good thing, a positive thing. So we did in fact learn something so far. So solvent bar speed, again, at 6.5 inches per second. In this case, we're going to test both 1 inch per second gantry speed as well as half an inch per second gantry speed. So the 4 particular tests or cycles. Test number 1 is a solvent vac dry cycle. Number 2 is a vacuum solvent vacuum cycle. Test 3 is a solvent vacuum. And the last test cycle was a vacuum solvent. Okay, so those are the 4 test cycles that were evaluated. And the results were very clear that test 4 yielded the overall best result. And it was also noted that test sequence 1 performed the worst. And I think it's important to note that that is actually the most commonly used sequence, and again, it yielded the poorest result. So going back to just a reminder of what those were. So test 1, poor performance, solvent vac dry, and the best performing sequencing was the vacuum solvent process. Test 2 and 3 weren't bad, but again, it did show us that drawing the vacuum, drawing the solder paste out, did in fact have that negative impact, as I mentioned before, about smearing on the stencil. So the next test was, so we've now kind of walked through more being better, more solvent being better, saturation, increasing exposure time of the wet paper to the underside of the stencil is important, and the sequencing was important, right? So we've proven all that. So the last phase of the testing was to look at, to try to answer the question, does a wet wipe process have a negative effect to the print process itself, quality itself. And for this phase of the testing, we utilized SPI, solder paste inspection, as a test metric, if you will, or method. Broken into two phases, a test 5A and a 5B. So 5A being a dry wipe process, no solvent. So this was a vac dry, and the wipes happened after every third print. Gantry speed at 1 inch per second. Test 5B is a wet wipe process, right? So we're using this as a vacuum solvent dry sequence. Again, every third board, 1 inch per second gantry speed, and the solvent bar speed of 6.5 inches per second. So let's look at these results. Results. So what this shows us is it clearly shows us that an SPI validates using 30 printed circuit boards consecutively. SPI clearly shows us positive results with a wet wipe process. And I say this is looking at CP and standard deviation. So we see CP increasing and standard deviation decreasing as we apply the, in comparison from a dry wipe to a wet wipe process. So that's what we're looking at here. We can see we're using capacitors as the components. We can see this is the dry wipe process and the wet wipe process. And we see CP increasing in the wet wipe process, and standard deviation is decreasing. So a more stable and a more consistent process when we go to a wet wipe process over that of a dry wipe process. So it does answer the question for us that using a solvent is not a negative when it comes to the underside wipe process in terms of print quality, but actually a positive. So in conclusion, again, a lot was learned here during this testing. And the first one really is that SPI does validate the assumptions that a wet wipe process is positive, and it validates the initial visual inspection work that was done in the first phase of the testing. It shows us that solvents, when properly used, do in fact improve the print yields and result in a more stable and consistent process. Higher yields and reduced defects can be achieved when we carefully adjust the exposure time with the appropriate solvent, paper, and cleaning parameters. And lastly, it shows us that, like all things, over time things change. And kind of I alluded to this in the very beginning. The solder paste materials have changed, the papers have changed, the wiper technology has changed, so too have the solvent. So it was important for us to take a step now and really look at this in today's world. And again, I think we found a lot of new information that came out of this study, and I think it will really help the industry go forward. There is always more work to be done. The next step that we would like to do is look at a similar test, but looking at water-based solvents and additional solder paste materials. So with that, I want to thank you for your time. I hope you found this informative, and Will, I'll turn it back over to you. Thank you.
Thanks, Rich. Thank you guys for watching this Tech to Tech session. If you would like to discuss this topic further or have any questions not answered in the session, please contact your local KYZEN regional manager or send an email to tech@KYZEN.com, and we will have someone follow up with you as soon as possible. And if you like this video, be sure to follow us on our social media platforms for more expert cleaning content.